So that's the controlled NOT gates, but we're going to want to have controlled any gates, just a controlled operation in general. So let's see how we could think about that. So since x is not, since poly x is the NOT gate, we can think about this C naughts, and we'll want to start writing it this way, as the controlled version of just the NOT gate. So I'll write that as C in parentheses x. So controlled X gate, controlled NOT gate. And we can think about what this is doing in a few ways. So this Cx on the basis state control target, I claim can be written in the following way. It's going to be the control x to the control acting on the target register T. Would you agree with this? What does this mean? So let's just reason through it. If the control bit C is 0, any matrix, anything to the power 0 is identity. So it's going to do nothing. So we're going to get C, T, and that's the same thing that we had here. If the control bit is 1, then I am going to do the NOT gate. So C is never going to change. I'm going to do the NOT gate to the target register. And then what that means is the NOTs of any bit can equivalently be written T plus 1 mod 2. Do you agree? It's just changing it from 0 to 1 and vice versa, and we just need to be careful with the addition, make sure it's modulo 2. Now this only happens if the control bit is 1, so that's the same thing as T plus C mod 2. Okay? So we can think about the control NOT gate in this way. And that's going to allow us to extend it to any other unitary U. So definition for any controlled U operation, where U is itself a single qubit operation, and we want to define the controlled version of this, we're going to do it in exactly this way. So on a basis, the control version of whatever this U is, acting on a control register and with a target register, will be the same thing, same definition, control U to the power C, acting on the target register. So this is how we define the controlled version of any operation, not just the NOT operation. And this is acting on a basis state, and this is how the textbook defines it. Of course, this is a perfectly valid definition. It allows us to extend it to any other state that we want to do by linearity. But it's often useful to have the following representation as well. So I'm going to give you an equivalent definition of this, not acting on a basis state, but just as a matrix itself. And I won't prove this to you, I'll just write it down, but you should be able to reason through why it's happening. So this will be the outer product 0, 0 tensor identity plus the outer product 1, 1 tensor whatever the gate U is. Okay. So these will work out to be equivalent, and it's really not too much work to see why that's true. Think about what's going to happen if the first register C is 0. So I'll have a ket 0 coming in from the right. Ket 0 coming in from the right is going to kill this bra 1, right? They're orthogonal. And it's going to leave this as 1. So I'd have 0 and then identity, nothing's happening in the case that C is 0. In the case that C is 1, the flip side of that will be true. So it's going to kill the first term because of the inner product with 0, and it's going to leave the second term. So in the case that C is 1, the unitary will apply to the second register. Okay. So these are equivalent definitions. You should know both of them, and it's pretty much the same thing. But sometimes, if you just want to think about what the matrix is or reason about it this way, this is a good definition to have at your disposal as well. You don't have to think about what it does on a basis state. You can just write it down in general. The notation in a circuit that we'll use for this is control, still being a solid line, and then we're not very creative in quantum circuits, so just a box with a unit. And in one more case, we'll have another symbol, and that will be for the controlled Z, which you'll see on a homework assignment. But again, this would be the control register. This would be the target register. And I'll note to you, it's pretty obvious, but whenever we write a gate down like this, we're assuming implicitly that the first register is the control one. Okay? It's actually more clear from the circuit, what is the control and what is the target. And that's one reason why we really like the circuit notation. But in the equation itself, we'll always assume that the first register is the one that's being controlled on, and then the second one is the target. If you ever want to reverse that, which sometimes you want to do, there's various notation that you could use for that. So this is just controlled U not specified. If I want to reverse the control, which is obvious in the circuit, so how it would look in the circuit is that, well, the control changes wires, and then the target is on the other wire. So now this would be the target. This would be the control. How would you write that mathematically? There's various ways. You could do a subscript, so controlled from B to A. So again, we're using our Alice and Bob analogy, or just the letters A and B. So the top wire being A, the bottom wire being B. And then the first one specifies what I'm controlling on. So controlled BA of an operator U, you could use this notation. You could also use numeric indices. So if you start this indexing the qubit as 0 in the circuit, then this would be a control from 1 to 0 of the unitary U, whatever it is. Okay. So in the circuit notation, this is not an issue. And again, that's one reason why we really like the circuit notation. Mathematically, if it's not implied, always assume that the first register is the control register, second is the target. If you need to change that, which sometimes you might want to do, then there's various notation that you could use for that.